So it was Justice Liebig in the mid-1850s who is argued to be the founder of analytical chemistry, the first individual to actually have a true chemistry laboratory, who said that the productivity, and in this context he was thinking about agricultural fields, but productivity in general is not limited by that resource that is least available in the environment, but instead by that resource which is least available compared to demand. So there's a lot of stuff out there that's not very abundant, but there's not a great demand for it. And so it doesn't become an issue in terms of growth and production. The two fundamental elements that do in the context of living things are nitrogen and phosphorus. Nitrogen, primarily because the dominant reservoir is in the atmosphere, in an inert form. And it doesn't occur in rocks to any meaningful degree. Phosphorus, on the other hand, tends to be common in many rocks, but it is geochemically sequestered or occluded, and thus it is often in short supply. So when we think about water quality, we think about limitations to growth in aquatic systems, we think about nitrogen and phosphorus. And that's the focus of my research program, and that's the biogeochemical component. And today I'd like to talk about a biogeochemical investigation to help us understand the food web of the Clark Fork River and how the restoration activities underway may or may not allow for restoration of in-river activities. Now, I will admit that when I was putting this together, thinking of my audience here in Butte, you are going to know a lot of the introductory material already, but I'll go through it in case you don't. The plot here is of the catchment that defines the upper Clark Fork River, and that river begins when Silverbow Creek and Warm Springs Creek come together at the Warm Springs Ponds. It then flows about 200 kilometers downstream until the confluence with the Blackfoot River defines the middle Clark Fork. By the time the Clark Fork leaves into Idaho, it is by far the largest river leaving Montana, much larger than the Missouri. Here, however, it can be a relatively small stream at its headwaters and then gains considerably, as I'll show you, as it goes downstream. You know this story well. And when I'm speaking to other audiences, they're often very surprised to find out how active an environment and an industry Butte was at the turn of the century. And the behavior among these three argued in many ways to advance the economy and resources, but also embrace some damaging approaches to protocol and process. And this has a great deal to do with the fact that there were no laws inhibiting a lot of how the materials were handled. As you know, the ores were derived from the richest hill on earth. They established the smelter at Anaconda to do the smeltering work, and this resulted in a large amount of tailings, processed ore, that were stored on floodplains in your streams. In 1908, one of the largest floods on record occurred when there was a rain on snow event that mobilized all of these mine tailing materials. Here's some pictures that are particularly effective for folks from Missoula, who all the students go downtown to the bars here on Higgins Street. And this was an extraordinary flood. They blew the dam below the Blackfoot to try to save the facility, and they couldn't. They lost it, but they rebuilt it. And then in 2005, they tore it out again. As a result of that flood, these tailings were distributed throughout the floodplain and transported all the way to the river's delta with Lake Pend Oreille in Idaho. That delta in Idaho is a Superfund site. The system we're talking about here is a collection of 4 Superfund sites. You guys know more about it than I do. That's called the Megafund site, and it's the largest EPA Superfund site in the nation. After this flood, and throughout the coming century, any real elevated flow inundated floodplains heavily laden with metals and could cause episodic fish kills and very detrimental chemical conditions in the river itself. So after some degree of litigation with ARCO and BP and the likes, the restoration program initiated on the Upper Clark Fork Operable Unit has begun, and that work is being organized from the Department of Justice through the Natural Resource Damage Program executed by the Department of Environmental Quality. Most of it is focusing on Reach A, and that's from Warm Springs down to about Deer Lodge, or actually just above Garrison. And the intent there is to address these sorts of elemental copper mainly deposits, sometimes called slickens, with such high copper content that vegetation is lacking. And this is being done by restoration techniques that will lower, actually, the elevation of the floodplain. Here's an example near Dry Cottonwood Creek, where the materials are removed down to the depth of the tailings and then replaced with what's called a vegetative backfill. That's basically the soils from the terrace with a little bit of mulch mixed into them, laid back into the floodplain, with the intent of lowering that floodplain because the deposition of the tailings caused such an A-grading, of material that the river was essentially geomorphically locked in place, unable to interact with its floodplain, which is an important aspect of river ecology. So our lab is generically asking, what are the long-term consequences of restoration for river communities and processes over the coming decades? Recognizing that the focus of the restoration is on the floodplain itself. The debate as to whether or not a water body should be dredged is one that reoccurs in virtually every restoration program. You may have heard of the PCB problems in the Hudson, and for years and years they debated whether or not they should dig that stuff up. They decided not to. The same decision was made here. The riverbed was left intact. So we have a river with the legacy of sediment contamination. We have a floodplain that's under restoration. Now that restoration process, as I mentioned, is focusing on Reach A, but there will be some manipulation in Reach B, and then there's a major concern about the characteristics of Reach C. And Reach C is not going to receive any direct remediation or restoration actions. But there are resources to address the issues in Reach C, and I hope to show how the upstream components of the river link to those issues downstream. We're doing this first by going back to historic data sets that were generated by a rider on a bill in Congress that funded what was called the Tri-State Water Quality Council. And it was Idaho, Montana, and Washington that had the funds to maintain an elaborate monitoring program all the way from Lake Pend Oreille up to Silver Bow and above. And these were sampled extraordinarily every 2 weeks for years and years. And then that money was lost, and the voluntary nutrient reduction program was taken up by the Department of Environmental Quality, who is still now maintaining monitoring, but only during the summer months and only at limited locations. My lab at the University of Montana was fortunate to receive funding from the National Science Foundation's long-term research and environmental biology program, along with some of my colleagues from Montana State. And what we did was go to the historical sites that are shown here as Roman numerals and pick up on the legacy monitoring and fill in when the DEQ isn't sampling. We are, in fact, we're overlapping with their sampling so we can cross-reference. The color scheme will go from darker colors at Warm Springs and then lighter, as you can see the sites go from upstream to downstream. Here are the data sets we're working with. One core important component is the sediment metals. These are total recoverable metals, meaning not dissolved, but those associated with the sediments. And this is in the riverine sediments. at these sites as a result of Johnny Moore and Heiko Longer's long-term monitoring of metals. So what we're fundamentally doing here is trying to combine an understanding of the biogeochemistry and its influence on growth, and how that then interacts with metal availability and the movements of metal through food webs and their consequences. Just to give us a rundown on the status of the metal environment. This is Johnny's data set, and he gave me all of his samples, and we're continuing his effort. What you're seeing here is three sites monitored from 1990 to 2012 by Johnny and his colleagues. And what you can see is that at the upstream sites, back in 1990, you had as much as 1,500 parts per million sediments in the riverbed. And you can see then as you move downstream, that peak concentration declines to about 1,000, and then even further downstream to 500. And that simply represents distance from the source and distribution of sediment laden with metals. The other thing you can see is that all of these are following an exponential decline. And this is a very interesting paper in Environmental Science and Technology where Johnny modeled the incoming of new sediments, mixing with sediments in the bed and sediments being transported out by the river. He predicted that the river will clean itself up in about 300 years. And the state wasn't very happy to hear that. But that is a model based on flow characteristics in the past, and his point was that you can change that if you remove point sources, as they are doing now. And then he incorporated that in the model. Another thing he emphasizes, here are the two main levels of toxicity that the EPA uses to address aquatic life. And you can see they're well, even as it's declined substantially over decades, it's well above that level. So we have a contaminated riverbed. In terms of nutrients, the dominant form of nitrogen available to the biota in the water is nitrate. It represents about 30% of the total nitrogen, and it is clearly the important player when it comes to plant available. That term simply means that it can fertilize life. And what you see with these data is that the upstream sites tend to be more nitrate rich, and they decline as you go downstream, as shown by the lighter signals. And there really is no particular pattern in nitrate per se, although it looks like there might be some decline later in the monitoring period. The form of phosphorus that we monitor is called soluble reactive phosphorus. It picks up inorganics and small organics. And this plot illustrates that there is an enormous quantity of phosphorus available in that river. A low number is 5 micrograms, or 0.005 on this plot down here. This is an extraordinary amount of phosphorus. And there's a very good reason for it. There's an exit on the way here called phosphate, and they mine phosphorus out of the rocks associated with Phosphoria formation. So the river is flowing through a relatively young sedimentary source of phosphorus, and it's full of phosphorus. So if we put those two things together, in thinking about nitrogen and phosphorus as limiting growth, we generate an atomic nitrogen to phosphorus ratio, mole-to-mole ratio. And we ask ourselves, well, how does the abundance of one compare to the abundance of the other, and what's the line that really matters? Well, this line right here is 16, and that's the composition of algae. For every 1 phosphorus, you need 16 nitrogens. So any points above this suggest you're going to run out of phosphorus first. Any points below this suggest you'll run out of nitrogen. And as you can see from that notation, there's about 800 points that are less than 16. More importantly, those numbers that occur above the line only occur when both nutrients are really abundant. So it's likely that nutrient availability isn't limiting at that point anyway. So that makes us think that the availability of nitrogen is the issue as it pertains to the quality of the water. And that relates to this. In order to measure the abundance of autotrophic biota in the river, we scrape rocks and we extract the pigment responsible for photosynthesis from them. So the standing crop, that is milligrams of chlorophyll A per meter squared, is a good measure of autotrophic abundance. The state went through a long process of determining what the water quality criterion for the river should be. And it's one of the first published in the nation anywhere for a river. And for chlorophyll, they decided it should be 100. And these are the averages from the monitoring program. That's what 300 milligrams per liter, or milligrams per meter squared looks like. But we will routinely see 600. And it almost looks like you could walk across it. When you're driving on I-90 and you look at the river, it looks kind of like the color of Mountain Dew. Iridescent, yellowish green, like it's going to crawl right out of the river. That's a lot of chlorophyll. And that means it needs light, it needs heat, and it needs nutrients. And the implications of that chlorophyll I'll come back to at the end. So in order to figure out how this river system is working in terms of supply and demand, we segmented the reach, the Upper Clark Fork, into 5 reaches, where each reach is bound at the top and the bottom by a monitoring site. So our reach effectively is an ecosystem. We've got inputs and outputs, and it's our intention to address those, the character of those inputs and outputs with distance downstream and over time to see how actually the river's working. One of the reasons we're able to do this is our sites are nicely located near USGS gauges, so we have rates of flow. And what this plot shows is that as you progress from upstream in the dark to downstream in the lighter colors, at any time, this is the average over 30 years, at any time when you move from one site to the next, it gains water. There's no time at which the river is, based on the averages, losing water from one site to the other. Now when you get into the individual numbers, I found about 8% of all measurements were losing. There are times when it's losing. I think that's related to irrigation withdrawals. They mainly occur between Warm Springs and Deer Lodge. But for the most part, it's a gaining river. What we can do then is use those measures to address loads. So you can think of a donor reach as one in which materials enter at some rate and far more exits the bottom of the reach. And it acts as a source of materials with a positive change in load. And you can contrast then that with a sink, in which materials enter the reach and the load leaving is lower. If in fact it's a losing reach, that may be in part due to water going away and taking stuff with it. But the vast majority of these observations suggest that's not the case. Then I've described the notion of a conveyor, one in which materials come in, it travels through the reach, and it leaves. And there's effectively no major change in the load. Now, you could also add what I call a collector. Imagine if all the upstream, if the upstream load came in with a certain flow and a certain concentration. And then in this reach you had tributaries with the same concentration. That load would increase. But it increases not as a result of production, but just of compiling water and materials. So it's collecting. And so we're trying to tease apart the behaviors of the systems. We'll do this by taking the concentration and multiplying it by the discharge. That will give us mass per unit time. We do a load in, load out minus load in. A positive value means an increase in load. So if there's no change, it's at material steady state. If it's positive, it's either accumulating as a result of inflow or it's producing. If it's negative, it's consuming materials or losing them through export. And as I've emphasized, that really doesn't seem to be the case here. We can assess these as absolute changes, or we could divide them by reach area and get a flux. Mass per unit area per unit time. The other way to do this is to address this issue of collector behavior. What if we predicted that the downstream load is the in-stream load increased by the proportional increase in flow? This effectively says that if it's 1, this is a result of hydrologic accumulation of water with the same concentration that entered the reach. It just got bigger, so the load went up as expected. If it's greater than 1, it's either being enriched by an external source or it's producing that material. If it's less than 1, it's either consuming it or it's receiving a flow that is far more dilute than that which enters the top of the reach. So we put these things together in the context of understanding whether or not we're gaining water, how our masses are changing, and how observed and predicted materials behave. Let's start here at the input to reach 1. These are the loads in kilograms per day, and what you see right away is an evident increase in the amounts of nitrate entering the reach in the winter months. And then associated with it is a drawdown during summer. And you can also see that the character of this over time really hasn't changed in this particular sense. I'll come back to this and revisit that same issue. Well, what about the changes in load? So here's what's happening as you move down the river. What we see is the maximum inputs to reach 1 occur during winter, as shown by the inputs, and then it's drawn down pretty predictably to almost zero change. And if we look at this across the entire period, it gains about 75 kilograms per day. It's a significant increase in material load. Now, if we look at the predicted numbers, you can see that it is 10 times higher than you predict from flow accumulation alone. And this is pretty consistent. We only see a couple of times when it appears to be lower than what would be predicted by flow. The other thing that's interesting here is that the greater values occur during summer, and it's close to predictable during winter when maximum materials come in. Over time, that represents about a 3.5-fold enrichment. It's either inputs of materials or production of nitrate in the river reach. Now, let's jump back a minute so you can see that these delta L's are positive robustly. The predicted are somewhere between 1 and 10. Let's go to reach 2. You see them jump all over the delta L values, many of them negative, some of them positive, and the negative values, again, are associated with the summer months. The average, in fact, is negative. So reach 2 is acting very differently compared to reach 1, and you see that in the predicted numbers as well. They're far less than 1, routinely with summer, and they average about 0.64. So flow is accumulating, but nitrate's going away. And that we know that both from these numbers and from the hydrology that goes with it. Flow, the negative, the reach that tends to lose is reach 1. Reach 2 is always gaining. So that tells us something's going on. If we put these together and take a look at the river all the way down, we have on the bottom the uptake, or I should say change, in that amount of material per square meter of riverbed per day. And what you can see right away is that reach 1 produces, whatever the season, at a fairly substantial rate. The asterisks indicate that they're statistically different from 0. Reach 2 then robustly consumes, and only in winter do we see it producing. Reach 3 during the warm months is a consumer, but releases in winter. Reach 4 is just sitting right around 0, whereas reach 5 appears to be producing some materials. And you can see that all of these numbers, well, most of them are significantly different from 1, except in reach 4, where there's very little activity. So we could kind of classify these. There's your producer reach, and then below it, we have a couple of consumer reaches, and I think the bottom ones are more like conveyors, except I gave that one a little production mode. And we'll get back to why that is. So there's spatially specific relationships to where the nitrate is accumulating or being removed. Here's the story for phosphorus. Look at in this case, the upstream reach is a consumer, and slightly higher than predicted. Whereas for nitrate, it was a producer. And then you see this area right in here. This is the Gold Creek Garrison area as you go through the Phosphoria formation. And the phosphorus just pours in to the river. Even up here, though, the concentrations are quite high. So here I would argue then that you have sort of a conveyor. a producer, and a producer, and maybe even a third producer, depending upon how you measure this, and then a conveyor. And that's understandable because phosphorus is going to be abundant beyond biological demand, and it should act relatively conservatively unless it's being added to the system. So look at the way these things map out. You have these flip-flops of where one is a source for one material and it's a sink for the other. And then they flip-flop as you go to the next reach. And we think that's really interesting and are asking the question, is the upstream reach influencing the downstream reach? Is there a linkage here that causes this flip-flop? So what we did was we plotted this is in the summer when biology matters most. Lowest flows, massive biota, warm, cranking. This is the degree to which that upstream reach acts like a donor over the record up to 2015. And this is the degree to which the downstream reach acts like a sink. The colors represent temperature. So you can see the highest loads coming out of one are associated with the most consumption downstream, and they're very closely linked. These are some interesting outliers, but it suggests that the upstream contributions to the reach 1 contributions to reach 2 are dictating how reach 2 behaves. Moreover, its behavior is changing through time. Here's the degree to which reach 1 acts as a donor. It's significantly increasing, even as the extent to which reach 2 acts as a consumer is increasing. Why? What's going on in the landscape such that that's the case? Well, we got in the canoe and we went from Warm Springs to Deer Lodge and sampled nitrate every half a kilometer, and there's the plots for October and April. And you can see a rather abrupt increase in nitrate concentrations right there. And that is Lost Creek, right where Lost Creek comes in. And the question then is, what is the character of Lost Creek such that it should be such an evident increase when we don't see other increases of comparable magnitude? Its contribution to flow is about 6%. And yet its contribution, it can almost double the amount of nitrate in the river. So there it is, and it's embedded in an agricultural component of Reach A. There are alfalfa plots, there are feeds coming in for cattle that generate manure. There's lots of reasons that nitrogen might be on the landscape. But if we zoom in on this, here's a plot from my student Patrick's effort. Here's Lost Creek, rumbling along the side here, and then it goes up into the mountains just short of Anaconda down here. This red outline is outlining what's called the Lost Creek Dutchman Complex. That is a giant buried wetland. Right upstream of it is the Anaconda wastewater treatment lagoon that isn't really operating properly. So what we're trying to figure out is the nitrogen budget here. Is it the case that this system, and here's a view downstream from it, when you core it, you'll see mineral materials with clays, but then if you walk over a ridge, you'll end up on a fen. And it's like walking on a trampoline, because beneath you, it's all organic matter. And we don't really know the depth of it yet, or the size of it. But if you think about it, fens and peat bogs occur when organic matter is being stored. That means there's more plant growth than there is decomposition. And it gets stashed down there. There's no oxygen, so the rates of decomposition are low, and organic matter builds up. That's the nature of peat. And that means you have to have active plant growth, right? But if you flood that and cap it with a meter or half a meter of mine tailings, so rich in metals that they're almost minable, the metal content on that complex is absurd. It's the only piece of land in the upper Clark Fork Reach that's still owned by ARCO. And it is tricky to get permission to get out there. I think that's the 800-pound gorilla. We're going to have to deal with that thing. And so we're wondering, is this thing rotting? And effectively, out from this organic matter comes all this, what was organic nitrogen, and it hits the stream and bleeds into the Clark Fork? That's the focus of Patrick's work. We're using the same approach in the fen. And what he's basically found is that the groundwater has virtually no nitrate in it. And there's no nitrate coming out of the mountains, but the groundwater is full of ammonium. When it hits the stream, it all gets nitrified and it pours out as nitrate. We don't know if it's that sewage treatment issue or if it's coming from there. So we're using stable isotope approaches to try to figure out source without mapping out an entire groundwater stream water model. But that might eventually be needed because the scale of the restoration is large enough that it should probably include issues of the warm spring ponds and the main channel itself. And Doug Martin, who runs the restoration program, is completely aware of this. And what he has done very well over the last 5 or more years, 10 probably, is engage different people with different expertise and says to them, oh, what should I do? And for us, as faculty members in the university, we get like gold stars if we publish a paper. So for 5 or more years, I was begging for money from Doug and the NRDP because I wanted to get in on this. It sounded really interesting. And I didn't get a penny. And it wasn't until I switched my thinking from how can I get money for my research to how can I help make this resource better, that I became part of the team and then funding starts coming my way. And I didn't realize that until I looked back on it. And what I end up doing now is I write reports. And I don't get very good gold stars from my faculty review. But I'm old. And I'm already promoted, and what are they going to do? Fire me? So what I figure out is like, write that report, because they got to make a decision in 12 months on what they're going to do with this money. You know how long it takes to get a paper published? Especially if it's a master's student who's writing it. Then you got to get it into review and get that will never work. So now what I've done is I sort of got my students, they have to write a report and a manuscript. And that means more time from me. But it's great. It feels like, you know, you're tied to a place that's important to you and you believe in. I was born in Polson. I got to come back to Montana. So it's really rewarding to help solve some of those problems. And the issue about nitrogen and its potential to promote algal growth is really about fish. That's really what the resource is. If you go to the Fish, Wildlife, and Parks and you ask, how are things in the upper Clark Fork River, they will give you the information on trout. They have these huge float boats with shockers, and they shock all the fish, and they only count the trout. So if whitefish come up or suckers, they're not quantified. Because the game fish is the economic issue, and they're resource limited. But if you want to put together an understanding of the river, suckers are important, sculpins are important, whitefish are important. We'll get back to that. But this is like, you know, we're right in the middle of the river run through it world. People come from all over the place for the Bitterroot and for the Blackfoot. In the Bitterroot, there's like 620 fish per kilometer. In the Blackfoot, not quite as many, 310. But if you go over the hill, have you all been into the Big Hole and floated the Big Hole? There's almost 2,000 fish per kilometer. It's extraordinary. That river is so productive that it foams from natural dissolved organic carbon. And the organic carbon in that comes from this big sort of flat wetland-like upstream environment. That's why they call it the Big Hole. Instead of a typical drainage, it's like cliffs and then a flat pan that's a giant wetland. Up near Wisdom, the soils are black. And it's great ranching. The only problem is they take the river and they break it out into all these irrigation canals. It dewaters, and it's one of the native grayling populations in there. So fish are really important, but we haven't even gotten to the best spot. Are there anglers in here? Where's the best riffle in Montana? It's in the Missouri. When these 3 rivers come together and go through these impoundments, they come out of the dam with the nitrogen and phosphorus available because they've been in those reservoirs, and they feed a 7-mile riffle in Craig, Montana that has nearly 3,000 fish, huge fish. And people come from all over the world to this little runway and fly in and get their outfitters and float that thing. So there's some numbers. How do they compare to the to the Blackfoot, or rather to the Clark Fork? Well, they're not good. I mean, these are not good numbers. So here we are, upstream to downstream, from right to left. This is a survey from the Fish, Wildlife, and Parks that Pat runs, back from 2015 back to 1987. And you can see the high values are associated with, back in 1987, if we remove those, our numbers are about, less than 200. In 2015, they're less than 100. And then look at Reach C. They're like 60, 80. That's orders of magnitude lower, and this is primarily brown trout, than all the rivers around it. And the idea is that the metals are killing the fish. But the problem with that argument is, look at the direction here. The best populations exist in the areas with the highest metal concentrations, and then they decline. The bugs do this too. More bugs up here and less down here. Then we're like, well, what's that story about? So what we think is happening, and here's where the Bitterroot and Big Hole fit in, and you can see we're well below it. What we think is happening in Reach C, and that these guys are concerned about, what features potentially contribute to that low standing crop? I think it's a food issue. I think it's related to too much algae and food problems.
I just got to point out that's not Daryl Reed.
That's not? Is that you?
That's me.
Hi.
I'm not, I've never gone by Daryl Reed in my life.
And you are?
Joe Griffin.
Oh, hi, Joe. Good to see you again. So there's Joe posing for That's embarrassing. I will admit, it's an old slide, but that's still no excuse, because I remember you giving us a tour at the pit years ago. Okay, so Joe is standing in for Daryl. And I'm not sure if Daryl's the right guy here anyway, that when you get into the DEQ, they have water quality spread across a bunch of different divisions. But as a team, as a group, the state's really going after this. So in order to figure this out, we got some money from the state to address Reach C. So this is right about where Flint Creek comes in, and this is just above Drummond, down to just above where the Blackfoot comes in. And we measure the amount of organic matter on the stream bottom by going in there with a hoop, pick up the stream bottom, get all the organic matter, dry it, put it in a kiln, burn it, so all the organic matter is gone, measure what's left, and by difference, we get what's called ash-free dry mass. And this is used in fields and forests and lakes and streams. And what we see is the development of this mat. I mean, there are rocks under there, but you wouldn't know it. And it accumulates until July, and then it begins to go away as it sort of senesces because it gets too warm. That algae is Cladophora glomerata, and it's notorious for having a seasonal progression. I had a master's student working on this, and he showed the same thing. If it gets a little bit colder, it comes back a little. So that's a lot of organic matter. Well, is it how much? I mean, is it a lot or a whole lot? So what we did, of course, was compare it to other river systems nearby, and it's orders of magnitude higher. There's way more organic matter in that stream bottom than there ought to be. The Bitterroot is also a sunlit, broad river, shallow, could well support a lot of algae, but doesn't. I do, though, think that the Clark Fork's always been very productive, but I think this is hyper. And so what we were concerned about is how that influences feeding. Can we turn off those lights so you can see the movie? Trout either feed here on the bottom, what's called epibenthic, the prey or the living on the bottom, or they feed from drift. And that's the difference between the dry fly and the wet fly. For the anglers in here already know all this. And there's a big debate about which fish eat which and which one's more important. So what we wanted to do was measure the suspended organic matter in the water and create an understanding of how much algae is entering the drift and what its implications might be. We used a very coarse mesh net because we wanted to look at materials that might be coming from the algae itself. Even using a coarse mesh net, the numbers are quite high. Here's Reach A and Reach B, and here's the movie of it here. If you look in the lower right-hand corner, you can see the trout swimming in, in racetrack is about here. And you can see cobble, and you can certainly see green materials, but a fairly clear water column. When you get to reach C, it's a different story. I always liken it to like driving a Jeep through the jungle and all the fronds and the palms are slapping on the window. We are trying to collect the invertebrates, but the net would clog with algae. There's just an enormous amount of material in the water column. So if trout are feeding in these two environments, we need to ask the question, how does that sort of behavior influence their ability to consume prey? And can it then support a higher population density? Is the food there? So we went out and we measured what is called the standing crop, or standing stock, if you're talking about animals. Number of animals or mass of animals per square meter. And when we look at those numbers, they're sort of typical to, with downstream parts. They're not really low. And then what we did was we took those bugs and we measured their metal content and we measured the stable isotopes of carbon and nitrogen in them. And using a Bayesian inference program, we could say, all right, build a mixing model where you take this bug with its signature and this bug with its signature, combine them in some fractional way that they will represent the trout. We had 14 trout in one and 16 trout in the other of different sizes. And then this statistical package puts together an assessment of what the trout are eating. The package in spring said, you've got two different food webs here. One of them's for the big guys and the little guys, and the other one's for the middle-sized guys. And I thought it was really weird. But then I have to admit I don't know anything about fish. So I wrote my colleague at Idaho State. He says, well, this happens all the time. These guys are really aggressive territorially. And the large fish will displace the smaller fish into a suboptimal habitat. And they'll get the best one for prey. If they're really small, the big ones don't really care about them. So the big ones and the little ones overlap, whereas the big ones and the middle-sized ones push each other apart. And so these guys were eating really evident prey that are associated with the stream bottom. This one builds a net. This one's notorious for staying close down on the rocks. And they had partitioned out their prey. These two different colors are with and without the use of the metals, isotopes alone in gray, or metals and isotopes in red. So in the spring, they're eating these things that we think they can get to. And then when you get to the summer, everything changes. There's only one food web, and they rely mainly on drift, and that area, they got to eat out of that. So in the summer, when the biggest thermal stretches occur, and all these fish have to go into the deep pools, they're overlapping each other, and they have to rely on drift. What we need to know is, okay, the organisms are there. We have a good understanding of what they're eating. But the question is it enough to grow a lot of fish? And what you have to do that is figure out not how much stuff there is, but how much it's growing. And then that gives you a production rate. So those are arrows. This is Wyatt Cross from Montana State. He's joined our team at Clark Fork, along with Jerry Downey, myself, Ben Coleman, Mike DeGrompre, and Libby Metcalf. The Montana EPSCoR program is giving us resources to go after these questions. And what we want to build is what he built here for the Grand Canyon. This is called the trophic basis of production. Trophic means eating. So what they're asking is, there's your rainbow trout. What's the flow of energy to it? What are the biggest, not how much is there, but what's actually being eaten, and how big are these arrows? Because from that, you can calculate how much of that you can grow. And I'm not sure what the answer is going to be, but that is not really healthy trout habitat. They tend to use rocks for hydraulic refugia, so they can hang there, not burn much energy. Well, those rocks are all carpeted over with algae. There's no place to hide. It's hard to get to the food. It's really hot. There's a lot of things about Reach C that are problematic. So we hope to be able to link the productivity of the river to those food web questions. So in conclusion, We need to think about the Upper Clark Fork operational unit in strategic pieces and use those pieces to think about where sources and sinks occur and understand to what degree does this have to do with in-stream behavior or linkage to the landscape through both groundwater and tributaries. The interactions among the sources and sink may really strongly influence those food webs, and we need to understand that. So the restoration planning, while it is focusing on metals, and rightly so, it must be considered in interaction with issues of productivity. And this is an area that not just river ecologists, but marine and lake ecologists are arguing about. It could be that very productive systems enhance the movement of metals into the fish, into the top food web, top levels, because it's very active. Or it could be, which is called the Bloom dilution hypothesis, it could be that very productive growth of organic matter dilutes out the metals. So those are some of the things we're trying to figure out and to help the state keep in mind as they continue to adaptively manage their restoration program. Thanks very much.